So today what we're going to talk about is something called the range of plausible values. And when we talk about plausibility, we're talking about whether or not something is believable or likely. So if you didn't do your homework last night and you come in and you tell me your dog ate it, I would say that's not plausible. It's not likely. It's not something that I'm going to believe. So we're talking about when we get data here, how much of that data can we trust? Because there are some situations where we might gather data that people have filled out incorrectly or people might have wanted to lie about. We discussed some different types of bias in the last video. So we're going to try to eliminate those responses by using this range of plausible values. And what I've got in front of me is the data from last year when my class ran this sample. We flipped a coin 20 times, and this is something we would have done if we were in class right now, but we're going to use last year's data instead. And I actually had the people in the room flip these coins and record how many tails they got. So each one of these dots represents a person who flipped their coin 10 times, and this is the amount of times they got tails. So for example, 4 people flipped their coin 10 times and got 6 tails. 1 person flipped their coin 10 times and only got 1 tails. So this data isn't just one coin flip on each one of these. Each one represents 10 coin flips. Okay, so in looking at this data, we at first glance are noticing it does sort of have that bell shape to it that we've seen a lot in this unit, but I want to know how many of these coin flips I would use if I were to actually study this data and use it for something else. So my first question is, does the experimental probability line up with the theoretical outcome of flipping a fair coin 10 times? And what I mean by that is this what you would have expected? So theoretically, what should happen? Well, we know that because coins are fair, the theoretical probability of flipping tails should be about 1/2, right? Which out of 10 flips would be 5 out of 10. So you could say that this lines up with what we expected because look which of these outcomes is most likely. So I would say, yes, theoretically tails should occur half the time, so this lines up with what we expected. Now keep in mind that although that is the outcome that happened more often than any other individual outcome, it's not the most common thing that happened, right? There are 20 times that this trial was run, and only 6 of those 20 times did we get 5. But we did get a lot of 4s and 6s, and so we got a lot of values that are close to that theoretical expectation. So if a person were to run one more trial of this experiment, which outcomes would you say are reasonable to obtain? And this is the heart of what we're going for here. So let's say that you each take your coins into a separate corner of the room, and you all come back and you tell me what you got. And one of you comes back and says, I got 10 tails out of 10 flips. Is that believable? Based on our data here, I would say that maybe it isn't, because no one here got that. Although that doesn't necessarily mean that it's impossible, it just means that it's really unlikely. So I might say I'm a little suspicious of that data. Maybe there's lying or cheating or something going on there. If someone got an 8, should I believe that? So what we want to do is have a mathematical way for determining which values are believable or plausible. And so we have a general rule of thumb that we use to determine the range of plausible values, and that's just that we're going to take the middle 95% of our data. And you'll remember that when we drew bell curves, that middle 95% happened within 2 standard deviations of the mean. So essentially what we're saying is we're going to take approximately this amount of our data, and we're going to say that the stuff beyond that is unlikely and therefore an outlier. Something along those lines. So let's figure out where is the middle 95% of our data. Well, if I want to find 95% of something, I'm going to multiply it by 0.95. So I'm going to take my 20 flips, or my 20 trials rather, 10 flips in each of those, and multiply it by 0.95. And that's going to give me 19. So what this is saying is, of the 20 trials, if I want to take the middle 95% of those trials, I'm going to keep 19 of them and throw one of them away. One of the 20 trials is going to get tossed. So it's going to be the one that's furthest away from the mean. And so what was our average, or the most likely value? Well, our theoretical mean was 5 out of 10, and in this case it looks like our experimental mean was also 5 out of 10. So I'm going to throw away the one data point that is furthest away from that theoretical mean, which would be that 1. So I'm not going to count that data. I'm either going to assume that that person cheated, or I'm not even going to pay attention to it because it doesn't necessarily matter. All right, when I study the data, I'm going to really look at the 95% of the data that's within 2 standard deviations of the mean, theoretically. And so the only numbers that I'm really going to count from this point forward are anyone who got a 2 or up to an 8, because those are the only data points that are within that range that I've just established. So from now on, based on this population, which granted it's a pretty small population, if somebody goes out there and only gets 1 tails, I'm going to be suspicious of that, and I'm probably not going to include that data in my overall study later on. Same thing if they get 9 tails or 10 tails. These are values that I'm not going to consider being a part of my range of plausible values. So the last component of this sample says, Mr. Earl pulls a coin out of his pocket and obtains 10 out of 10 tails. What might this outcome suggest? Well, because it's not within our range of plausible values, either this is suggesting that the coin I used is unfair, or that I cheated, because 10 out of 10 is outside of the range of plausible values. And we all know that it's possible to get 10 out of 10. It's just really unlikely. And based on the sample of data we're looking at, that's outside of what we would expect to take place. So what I want to show you now is the way that this activity we're going to run is going to function. So what you're going to be doing on Delta Math is the rolling the dice activity. And we're going to do the exact same thing that I just simulated with the coin flips, but we're going to do it with dice rolls. So the way that this is going to work is you are going to roll 10 dice at a time, and then you're going to submit the proportion of those that came up 6s. All right, so I'm going to roll, and it says here, number of rolls 10. So I'm going to roll the dice and click that button there, and here are my 6 dice. And so it's asking for the proportion of my roll that came up 6s. I only see 2 6s here, and 2 out of 10 would be 0.2. So I'm going to say that this was 0.2 for my proportion, and I'm going to submit that. And you're going to notice a little data point come out of the corner and land right there, just like in the simulation that we drew on our notes. And I'm going to do it again. And I'm going to roll the dice, and I'm going to come up with how many times I got a 6 here. 3 of those are 6s, so I'll put 0.3 and submit that data point. One thing you should be noticing as this is taking place, in the upper right corner, it's keeping track of how many simulations we've run, so how many times we've run this study, what the mean value is, and what the standard deviation is of this trial that we've run so far. And so we're just going to keep doing this until we can get a reasonable sample size. So I've rolled the dice 3 times, and I've got 3 different data points. And your homework is going to be to run this simulation 20 times. I need you to do it 20 times, and I'm also going to outline this in the slides. But as you do this, you're going to see all of this data come together with each other. So you'll see other people's data points on this along with my data points here, and we'll collaborate and get a big sample of data that we'll actually be able to trust. So this is what I need you to do before Tuesday, and on Tuesday in our notes video, we're going to study these results.